Last time we talked about the law of sines. So this time we've got to talk about the law of cosines, right? Right. So here we see a right triangle. And do you know what I think of whenever I see a right triangle? The Pythagorean theorem. So with this triangle, here's angle C. It's the right angle, the 90-degree angle. So the side that's across from that, side C, is the hypotenuse. And the Pythagorean theorem tells us that c squared is equal to a squared plus b squared. Okay, but what if this wasn't a right triangle? What if C wasn't a right angle? What if it was either less than 90 degrees or more than 90 degrees? Then it would no longer be true that c squared equals a squared plus b squared, because that's only for right triangles. But what would be true is that c squared equals a squared plus b squared minus 2 times a times b times the cosine of angle C. So that is what's called the law of cosines. There's really only one cosine in it, but okay, it's the law of cosines. And that's true of any triangle. Now, if this were a right triangle and C were a 90-degree angle, then the cosine of 90 degrees is 0, and then this part of the equation just goes away and you get c squared equals a squared plus b squared. But if C is something other than 90 degrees, then the cosine of C is something other than 0, and the equation is still true no matter what angles are involved. Now, since C doesn't have to be a right angle, it doesn't really matter how we label the angles, which one's A, which one's B, which one's C, which one we look at. So we could write that law of cosines in any one of three ways that just involve different arrangements or labelings of the different sides and angles. So we could say, like we just were looking at, c squared equals a squared plus b squared minus 2ab cosine c. Or we could say b squared equals a squared plus c squared minus 2ac cosine b. Or we could say a squared equals b squared plus c squared minus 2bc cosine a. Either way, it's saying any one side squared is equal to the sum of the squares of the other two sides minus 2 times those two sides multiplied together times the cosine of the angle between those two sides and opposite or across from the side you started with. And then any one of these could be algebraically rearranged to solve for the cosine part to look like one of these. So if you start with any one of these, just picking a different angle to be the angle that you have the cosine of that's between the two sides gets you one of the others, and then algebraically rearranging and solving for the cosine part gets you one of these. So they're all different variations of the same equation. Now let me show you a proof why this law of cosines is true. Now, if you don't care why it's true, that's okay. You can use the law of cosines without worrying about why it works or why it's true. You don't have to prove it, but somebody has to prove it. There has to be a proof in order to be a valid mathematical theorem or formula that you can use. So I feel obligated to show you a proof, and you can pay close attention or not. If you don't, I don't think it will hurt your ability to use the law of cosines, but here's the proof. And the version of the proof that I'm going to show you is kind of algebra-y, and I've seen other proofs that are more geometry flavored. I might link to one of those that you can look at if you like that approach better. But here's one approach. So take your triangle and set it in the xy plane so that vertex C of the triangle is sitting at the origin, and then the side of the triangle that connects C to B, so that would be the side across from angle A that we would call side A, is lying on the positive x-axis. So if one corner of the triangle is at the origin, and then this side has length A, when we get to the end of that side, we are at the point A0, the point where the x-coordinate is A and the y-coordinate is still 0. Then the third vertex of the triangle up here at angle A, we don't know where that is. We'll just call it XY for now. So the angles are A here, B here, C here. The sides are A, B, and C. The way I've got the picture showing, C happens to be an obtuse angle. Looks like maybe around 110 degrees maybe, but nothing that I'm going to say depends on that. C could be acute, obtuse, even a right angle. Now, the distance from A to B, the distance from vertex A of the triangle to vertex B of the triangle is using the, it's the length of side C. So one way of saying what that distance is it's just C. It's that side of the triangle. But another way of saying what that distance between those 2 points is would be to use the distance formula and say it's the square root of this x-coordinate minus this x-coordinate squared plus this y-coordinate minus this y-coordinate squared. So C, length C, that's the length of this side of the triangle, equals the square root of x minus a squared plus y minus 0 squared. I can get rid of the square root sign by squaring both sides of that equation, and then it would say C squared equals x minus a squared plus, and instead of writing y minus 0, I just wrote y squared. Now, if I multiply out the x minus a squared, I get C squared equals x squared minus 2xa plus a squared plus y squared. Okay, now remember back in chapter 4 when we were looking at definitions of trigonometric functions, one version of those definitions we used were take any angle in standard position with the initial side on the positive x-axis and then pick a point xy on the terminal side of the angle. So x is the x-coordinate, y is the y-coordinate, r is the distance that that point is away from the origin, and then for that angle, the sine is y over r, and the cosine is x over r, and so forth. So we could define the 6 trigonometric functions that way in relation to x and y and r. So here we do have an x and a y for this point that is on the terminal side of the angle C, and the distance from that point xy to the origin, what we were calling r, here we've got that labeled as b. So we can say that the sine of this angle C is the y-coordinate over the distance. So here that would be y over b. And the cosine of angle C is the x-coordinate over the distance, x over b. And then rearranging a little, we could say y equals b times sine C, and x equals b times cosine C. Okay, so now going back to the work we've done so far, and sticking in place of x, we can put b cosine C, so here and here, and in place of y, we can put b sine C, so now it looks like this. Now, where we've got a b times a cosine C and the whole thing is squared, that means b is squared times the cosine of C is squared. Same thing over here, b times the sine of C, the quantity squared would be b squared times sine squared C. And then here I just rearrange things a little. It's minus a 2 times an a times a b times a cosine of c. Okay, this is starting to look kind of law of cosines-y. We're not quite there yet, but we've got one more trick up our sleeve. I'm going to rearrange things to put the a squared term first, and then take the two terms that involve b squared and factor out their common factor of b squared. So it looks like b squared times the quantity cosine squared c plus sine squared c. And then we've got our minus 2ab cosine c. Now, look at that part inside the parentheses. We've got a cosine squared plus a sine squared. And remember that famous trigonometric identity that says that sine squared plus cosine squared is just equal to 1. So this is really just b squared times 1, and that does it for us. C squared equals a squared plus b squared minus 2ab times the cosine of c. So that kind of proves that this works. That's the version with the cosine of c, but we could have relabeled the angles or turned the triangle around so a different angle was sitting at the origin, and we would have gotten the same thing but with the letters in different places to get one of those other versions of the law of cosines. So I'm going to end this video right here, and then we'll come back in part 2, and now that we've got our law of cosines to play with, we will use it on some actual triangles to figure out some sides and angles. See you then.